Good afternoon, everyone. Couple quick announcements. I know some folks weren't able to join last week because of the power outages. And so the lectures are recorded. And so when you have a chance, please go back and review the lectures if you weren't able to attend. Also, the project proposals are going to be due on Friday. I have gotten a couple emails from some of you guys, and I will be responding shortly. Sorry, there's been a delay in that, but if you haven't reached out yet, please make sure to do so before the proposal comes in on Friday, so that I have a chance to give a little bit of feedback. Yep. Other than that, if there are no questions or any comments about the project proposal or homework, we can start today's lecture. So the topic for today is going to be about forecasting and technology diffusion. A lot of what we've talked about before is thinking about economics and finance and decision-making tools that play a role into how some of the new technology may end up getting integrated. But in this field of energy and transportation, where there's a lot of sort of rapid changes, there are a number of kind of more specific approaches and tools that folks use to think about adoption of new technologies. And that's because it's so central to sort of the future development of the energy and transportation systems. We'll be trying to cover some of that in a little bit more depth today. So data-informed approach when we think about forecasting and technology diffusion, and this is inherently kind of like a catch-22 situation, right? In that you want to use the sort of best data available in order to think about how technologies in the future are going to be adopted. But obviously the caveat is that if there isn't any data about how those technologies are sort of integrating into our society, then how can we have a data-informed approach? And so what we'll be talking about today is thinking about some ways in which we can leverage things that we know today in order to figure out things about tomorrow. So how do we know about what happens in the future? Right, forecasting can be random guessing. In other words, sometimes it just sort of gets made up sometimes, or informed guessing, right? So using past knowledge to predict the future. There are lots of different approaches that you can do, and a lot of these have their own particular strengths and shortcomings, which we'll try to cover as much as possible in sort of a qualitative sense. And we do want to try and be informed as possible when you are sort of quote unquote guessing, right? And so this is never to say that any sort of like projection or forecast that you're using with or making with this sophisticated model is necessarily going to get you the right answer. And in fact, one of the big problems of doing these kind of projections and forecasts is that oftentimes you can never really test your hypotheses. Oftentimes it's infeasible to like wait around and see if you got it right, or the types of things that you're projecting or forecasting could be one scenario of many which don't actually end up happening. But it can be useful, right, in helping understand sort of the landscape of possible situations that could occur, especially for policymakers or stakeholders who may have less knowledge or experience about this particular area. So all of that having been said, it's basically kind of to say there is value in making projections and forecasts, even if those projections and forecasts end up not being what actually happens. Okay, so here is kind of a basic list of forecasting methods that are fairly common in the literature and studies in this area. So fairly simple methods where you just do averaging, or drift methods where they take sort of segments or time slices of historical data and kind of extrapolate them. And then with the drift methods, that might be like a mathematical formulation that has random direction, and so things like Brownian motion, where you can extend things out based on some kind of algorithm that injects sort of noise into the forecast. Then there's time series methods, so moving averages, autoregressive moving averages, extrapolation, growth curves. So we'll talk about some of these. Econometric forecasting, expert judgments, and then we move into a more sort of large-scale predictive field, especially in things like machine learning, neural networks, and other sorts of simulation. We'll mainly today be talking about these sets of techniques, but if anyone has any questions about other types of approaches, I'm more than happy to discuss it. So I will say kind of off the bat that what we're doing today is more kind of like a high-level introduction to some of these techniques, and more in order to get a nice qualitative understanding. There are specific classes that you can take that dive into a lot more detail, both in theory and in practice, for a lot of these things. And in fact, like, you could take an entire class just on time series methods. So we obviously can't like get super in depth about how everything works today, but hopefully this lecture you'll walk away with enough knowledge to sort of understand what's going on, and for some of these, yeah, even sort of implementing them. I do actually teach a class called Applied Data Analysis next quarter, which teaches a lot of this stuff in practice in a lot more detail. So if you're curious about that, yeah, I'm happy to send a syllabus. Okay, so regression. So this is a statistical process for understanding relationships between sets of variables given data about those variables. This is a widely used technique in all sorts of models, both top-down and bottom-up, and kind of lays the sort of foundation of figuring out what you can understand about relationships in your data. So the simplest form of regression, very common technique, and very sort of widely used, especially in the econometrics field in economics, is linear regression. This is the basic structure for a regression equation. Y equals beta 1 times x1 plus beta 2 x2, and so on and so forth for however many variables. And let me describe what these are. So Your y is known as your response variable. It's often referred to as independent variable. Your x's are your explanatory variables. And then the betas are coefficients, which describe the effect of your explanatory variable on your response variable. And so if you think about the equation for a line, right back from high school, y equals mx plus b, this is essentially the same thing where it's telling you the relationship as your x changes, how does y change? And then lastly, you have an error term, epsilon, which is anything that affects y besides x. Okay. So this is an example of an ordinary least squares linear regression. That's also known as OLS. I'll talk about why it's called that in a second. And so this is the relationship between weight and fuel efficiency for a car. So this is just from a regular data set. I think this is actually the default data cars data set in R. And here you can see on the x-axis the curb weight, in other words, how heavy the vehicle is, versus the fuel efficiency. And so you have all these different dots here, which represents, each dot represents a single vehicle. And that vehicle has a particular weight and a particular fuel efficiency. And so there is some kind of trend that exists between the curb weight and the fuel efficiency, right? And so I could actually draw a line through this data, like so, to try and understand that relationship. Actually, I have the actual line here, which is pretty close to what I drew. And so this line is kind of the average relationship that's being captured by the trend in all of these points. And so the equation for this particular line is y equals 1.56 plus 0.0046x. And what that represents is these coefficients tell you that as the weight of the vehicle increases by 1,000 kilograms, the fuel consumption increases by 4.6 liters per 100 kilometers. And so this is telling you the slope of this red line, which represents the linear relationship between your curb weight and the fuel efficiency. Let me actually go back. So there's one quick thing to note is that this is just one sort of particular fit of this data. Okay, and so you can imagine there are lots of other possible lines that I could have drawn. So for example, like here, or like here, or like that. And so there's this question of why is this one, like how is it that we came about to get this red line, and why is this red line quote unquote better than any of these blue lines? And the main idea is that, and where the ordinary least squares term comes from, is that I can go from point to point. Let's say I pick this point here. I can calculate the distance to my red line, or actually to any line, right? And I can do that with any number of points that exist here. And if you think about what that means, it's basically saying, okay, each of these points is off the red line by some amount, which indicates the sort of error in the model for any particular point. It's known as a residual. And if you add all of those up, right, the total size of that error is going to be different for any particular line that I've drawn. And it turns out that this particular red line that is generated using this ordinary least squares method is the smallest total error among any sort of straight line that you could draw. There's one other thing that they're actually doing, which is they're squaring the value, right? And that's because you have some positive errors and some negative errors, and if you just add them all up, they're going to end up canceling out a lot of the error, and so that's why you square it. You could actually do the absolute value. Does anyone actually know why they don't do absolute value for linear regression, and why they square it? So it's actually an artifact of the calculation. So nowadays it's easy enough to do because the computers can solve it, but the sort of solution for solving something with an absolute value is basically computationally more difficult than doing it with a squared, and then the closed form solution is actually easier and more straightforward to generate. And so that's probably the sort of predominant reason why we do ordinary least squares as opposed to like ordinary absolute value. Yeah, so a bit of trivia about linear regression. And so we won't talk about this too much today, but there is also other ways that I could fit a pattern to these points, right? That's not necessarily a straight line, right? I could draw something like that. And so just one of the things that I'll sort of just point out for folks to remember is that when you do a linear regression, you're assuming a functional form that is a linear relationship between your response variable and your explanatory variables, which may or may not always be the case, but it is important to remember that that is one of the sort of underlying assumptions about linear regression approaches, and we will talk a little bit more about that in a bit. Okay. Any questions? Okay. So a couple. Again, this is we're moving kind of at a lightning fast pace here, especially for folks who haven't had as much exposure to this type of approach before. And so what I want to do is kind of just highlight a couple issues to carefully think about if you do end up employing this approach. And actually some of these issues are not discussed as much in sort of classes where you or you're learning about fundamentals about regression. And so I think there's value in highlighting some of these sort of concerns. So correlation versus causation, linearity, which I just talked about, collinearity, and data size. And so we'll go through some of these concerns one by one. One of the things to really note is that, right, I'm sure all of you guys have heard of this, correlation doesn't equal causation. And so when you are interpreting results from these sorts of regressions, unless they've done sort of a very rigorous approach about demonstrating this exact point, those coefficients never really, those coefficients don't represent a causal mechanism for any particular outcome. And so don't be fooled, you know, when you have like a really strong coefficient with like high statistical significance, that doesn't mean that one thing is happening because of another. There's a pretty funny website called, I think it's called Spurious Correlations, where some guy compiled a bunch of data points that he basically just scraped off the internet, off of random places that have, you know, open data sets to look for this exact sort of spurious correlations, where it looks like they're really closely linked, but in fact, when you think about what the actual interpretation is, then it makes sort of no sense at all. So this is an example. These all have like R squared that are higher than like 0.9. So this example is the amount of money that US spends on science, space, and technology correlates with suicides by hanging, strangulation, and suffocation. Okay, there's a whole bunch of other sort of silly ones. This is another one where the relationship looks really close, right? So again, if I plotted this kind of like on a XY axis, then the points would look to fall on a fairly straight line. So this is the number of people who drown by falling into a pool versus the number of films that Nicolas Cage has appeared in. Yes, okay, I see GTO's it's providing the link in chat if people want to look at more examples. Just a couple more. This one, again, looks pretty closely linked. This is the age of Miss America correlating to murders by steam, hot vapors, and hot objects. Okay, so you guys kind of get the point here, right? So you know, replace these with real sort of variables and both explanatory and response variables that you might see out in practice, and remember this, right? That just because the relationships are really close doesn't mean that one thing is leading to another. Okay, so the other the other point that I was making earlier about linearity and the relationships between variables, one of the things that you'll probably find is that there are very few sort of really obvious linear trends. Okay, and so this is so very few linear trends that exist in reality, in the real world. And this isn't to say that you can't apply linear regression approaches to these type of trends. Oftentimes, like economists will we'll do transformations on your variables to make them linear, right? And so that is totally fine, but it's remember that one of the reasons why you do that is compared to a lot of nonlinear approaches or non-parametric approaches, that forming your linear equations and solving them and interpreting them is oftentimes a lot easier, and that's why we tend to choose that's why that particular approach is tended to be favored compared to maybe some other approaches that you might see in statistics or machine learning. But again, it's always very important to remember that you should try and represent the functional form as closely as possible in your sort of regression approach. Okay, and so there's a question, you know, GDP over time, is this linear? Would I be able to approximate, you know, GDP as a function of time? What about for, let's say, oil prices, right? Would this be something that you'd be able to control with just time? And you can see, right, there are things that are happening that may indicate either one, time itself is not necessarily a good indicator, or that you need to control for other sorts of things that are happening. And so when you look at regression approaches that are assuming a linear sort of functional form, like try and keep in mind what the overall sort of data looks like and whether it makes sense to do that. Another one, so this is kind of harkening back to thinking about technology adoption. A lot of models will do some sort of regression-based approach where you look at you know, previous months or time series of data to extrapolate out like trends via regression approaches. And so if I wanted to look at the total cumulative number of electric vehicle sales, you could do that with this data, but you do have to be careful that, okay, if I just look at sales versus time, this is probably not a linear trend, and so you might want to do some kind of linear transformation on this X data. And so one of the most common ones that people do is that if it looks like it's doing some kind of exponential growth, then you can take a log of the data, and that would very often sort of linearize things. And so when you take that kind of approach, again, like think about the relationship of the variable, your x's to your y's, and whether that reflects kind of a linear pattern in the data. And if it doesn't, then you either need to do some kind of transformation, or you need to take a different approach that looks at that models the data in a nonlinear way. And so some approaches that you can do this is using semi or non-parametric regression approaches. So instead of assuming linearity or some predetermined structure, right, where you have betas, there are lots of non-parametric regression models, such as Kriging, kernel regression, and semi-parametric models, which combine both of these. So, okay, backing up sort of at a high level, the parametric models tend to be, so things like a linear regression, they tend to be easier to estimate, easier to interpret, but they make a lot of assumptions about the form of the model. Whereas with non-parametric approaches, you don't need to have that sort of assumption. Oftentimes, the predictive ability of these models is quite a bit more robust. In other words, the way that a lot of these models are able to predict certain outcomes tend to be really based on its ability to do prediction out of sample. You like calibrate it to its ability to make really good predictions, essentially. And so that's one of the sort of big pluses of these approaches compared to parametric approaches. But on the other hand, a lot of these results are not as easy to interpret, and it can be difficult or complex to, computationally complex to estimate some of these models. Okay, and so again, these are more kind of high level warnings and signs to watch out for or think about when you are employing regression-based approaches. So let's talk about doing forecasting. So really, it's a simple matter of doing predictions with sets of inputs. And practically speaking, when you're doing like regression-based forecasts and approaches, probably one of the hardest things to do is getting a good sample of input data that you can use to actually do the forecasts. And there are a couple sort of fundamental difficulties about doing this. As I mentioned before, with new technologies, for example, with one that I'm very familiar with electric vehicles, you know, when I was in grad school, there weren't as many vehicle sales around this type of technology. And so the amount of data that you have to calibrate these sorts of models is very limited. And that can make it very difficult to estimate coefficients accurately and understand the sort of real trends. So it ends up becoming this thing where you don't actually have a good amount of data until there's a length of time where the technology has been out long enough for you to do these sort of calibrations. And so when we think about these regression-based approaches, especially if you're looking at like sales data or deployment data, the types of things that, the type of technologies that this type of approach kind of really makes sense to do is it is for technologies that have been around long enough where you have data to work with. And so for things that either don't really exist yet or have been sort of available for such a short amount of time that you can't really calibrate the model to, this regression-based approach is going to be sort of a lot weaker. And then in addition to some of the issues that I was talking before, specifically with forecasts, there are some things that you need to think about carefully. One of the common things is thinking about the training range of your model. Okay, and so what I mean by that is, let's suppose I have some data like this. Okay, and I have a couple data points like this. And you figure out your sort of relationship here. But if one of the things you need to be really careful about is if your x is some measure of time or something like that, and you want to extrapolate out your trend really far. One of the big worries is that, okay, when you actually get to the future, what if it no longer looks linear, right? And then your prediction is really, really off. And so this is one of the particularly challenging things about these regression-based approaches, is that when you do these forecasts, you may be thinking about training the model to ranges outside of what you observe in the data. And that can be problematic for this exact reason. Oftentimes, it's kind of inevitable when you're doing predictions into the future, but there are oftentimes what people will do is thinking about like qualitative arguments for why this sort of thing might not happen. Okay, how are the assumptions of the inputs drawn? So thinking about your input data, are there any particular assumptions that are being made now that may sort of change in the future? And these are items that may be true today, but maybe not in the future. So one example of this is if anyone is doing and familiar with choice modeling, for example. So if you calibrate, I'm going to go back to the example about in transportation. If I'm deciding between like a gas car and an electric car or other technology, when you do these sort of choice models, the input values for electric vehicles, so attributes about its like price, its range, those may exist at a certain level today, but maybe really different in the future. And so you need to adjust for that when you're doing forecasts. And then also things like attitudes about technology. When you do historical based approach, when you're using historical data and doing those sorts of approaches, if you're factoring into the data how people sort of perceive the technology, that may bias your outcomes for the future, because you're also assuming that those attitudes sort of stay static. And then lastly, the thing about correlation versus causation, you need to be, if you are doing like causal based mechanisms, or you're doing like instrumental variables, for example, in an econometric approach, it's important to keep in mind, which coefficients and factors are actually directly sort of causing a specific effect. And that can lead to particular types of outcomes, especially if you're changing assumptions about your input data into the future. Okay. Any questions so far? Why don't we actually take a break at this point? We're about halfway through the slides, so this is a good time. So we'll do a quick 5-minute break, let everyone digest on regressions, and I'll be here if anyone has any questions or comments. Okay, let's continue on for today. So methods of projecting technology adoption or diffusion or market penetration. So the econometric modeling, a lot of the regression-based approaches sort of fall under here. I'm going to talk about diffusion models in a second. So S-shaped penetration curves, stock turnover models, and even logit models, which we use for things like choice modeling. Technically, these are all sort of regression-based approaches. All of the sort of bottom three points here are all kind of subsets of regression-based approaches. These S-shaped penetration curves are a particular subset that is focused particularly on doing this sort of adoption, whereas everything I've been talking about before, regression, like linear regression, is more sort of just a generic tool for data analysis. But we'll get into some specific examples in just a moment. Before we talk about that, and get into specifics about application of these regression-based approaches, I did want to talk about something else known as expert elicitation, which I'll mention because a lot of these sort of qualitative approaches can actually form the foundation for some regression-based approaches or data that you get from things like expert elicitation or other qualitative approaches can be leveraged in some of these methods as well. So I gave an example of this, I believe, in an earlier lecture, but this is, I think, probably one of the more well-known examples in my field, thinking about electric vehicles. And so when we think about doing this sort of modeling, and a lot of the drawbacks that I was discussing about not having data or data that doesn't really sort of help inform the future because of like changing conditions and that sort of thing. One way to get around this is you kind of just basically ask experts in this area. And so this is a lot more structured. Again, this is a high-level introduction to this, but expert elicitation in itself is a fairly well-known and developed field. And essentially you are asking authorities on subjects that have a lot of uncertainty. And so they're able to think about a lot of these uncertainties and incorporate it into their projections and forecasts. And they can give opinions about things that may be very difficult to model because data is not really available. But at the same time, right, even experts can be wrong. And so what I was pointing out with this particular figure, in case you forgot, so this is a figure looking at battery, lithium-ion battery costs for use in electric vehicles. And so there's $1 per kilowatt hour. And these are a bunch of experts who made projections over time. So this is a pretty famous study that was published in one of the Nature journals, so Nature Climate Change. And the experts provided a bunch of sort of range of values of what they thought battery cells would be costing in the future. And that price was estimated incorrectly, essentially, or predicted incorrectly. Nowadays, the prices is actually sort of below this red line, or sort of at or below this red line, and so you can see that the vast majority of experts were wrong. And so in this particular extreme case, you know, you're getting differences in reality with what experts were predicting. But in general, there are lots of good reasons for why an expert may predict a certain value, and they have a lot of information about the field, right? Which doesn't mean that they're always going to be right, but oftentimes it's kind of your best informed opinion. Okay, so that's kind of really this first sort of idea stage where you're really talking to experts and thinking about without any available data, how do I incorporate uncertainty about the subject and think about getting actual sort of values. And then, as I mentioned before, as we sort of move up this, where you have more and more data available and you have a better understanding of the technology, you can apply sort of different methods to understand how the penetration will happen. And so we've talked about some of this stuff, so the surveys or subjective estimation through expert elicitation. We've briefly sort of covered some of these econometrics or time series models. And so now we'll talk about some of the diffusion-based or cost-based models and historical analogy, which I actually tend to lump in with diffusion models. But yeah, I can see there being a case for kind of separating some of these. So for cost models, this is a lot of what we have covered already in terms of thinking about adoption as a function of the economics of a particular technology. So thinking about net present value, total life cycle cost, levelized cost of energy, and then sort of in the decision-making process, you know, internal rate of return, payback periods, discounted payback periods. And so these will often go into some kind of cost model, so where you may be comparing several different technologies and thinking about, you know, as the prices change, like you may be more or less likely to take in or deploy a particular technology using a lot of these techniques that we've already discussed. And so project selection, investment decisions, all of these things, all of these cost models factor into the decision-making process for those types of models and systems. Okay. Diffusion models. So this is, I'll give a couple examples: S-shaped penetration curves, stock turnover models, nested logit models. These are just a couple different highlights that we're gonna touch on, but there are lots and lots of different diffusion models out there in the literature, and you know, we're just touching some of the more popular ones, but this field itself is also sort of quite broad, and so there are different diffusion models that generalize across many different technologies, and then there are diffusion models that are built specifically to think about adoption of a particular technology. So we'll think more about the former, but if you are doing any of this stuff in your research or work, it's always good to, you know, try and see if anyone's done diffusion modeling specifically to the technology that you might be interested in, because there may be some kind of sophisticated models that already exist to do to look at deployment and adoption of that technology. One of the things that really drives a lot of the theory behind diffusion is that the patterns of technological change tend to look somewhat similar. And so this is a nice kind of example at a really high level that shows the pattern of energy substitution between different primary energy sources in the United States. And what you can see here is that, yes, so the kind of magnitude of energy use tends to be pretty different among my different primary energies, but you typically end up getting some kind of shape that looks like this, right? And that's been fairly consistent throughout all the different technologies that are being used today and in the past. And so the point of most of these diffusion models is to leverage the fact that we see these sorts of patterns. So to that end, it is actually pretty similar to a lot of the time series extrapolations where we're using, right, historical patterns to extrapolate future adoption or penetration of a particular technology. So that's all the stuff that we've been talking about in our regression models. But because we tend to observe a particular pattern, a lot of scientists have essentially figured out that, hey, we can come up with like a particular functional form that's not just sort of linear, right? That we can make really specific to adoption of technology. And so just a couple examples of this. So in this case, this is looking at GDP per capita compared to ownership of vehicles. And so you can see that there is a sort of really particular effect that we can sort of figure out and measure, right? And so I'm not breaking down any of the equations yet, but you can see that there is a series of trends that have been developed with uncertainty, right? In your in these lines. So we're able to essentially come up with some kind of diffusion model that will capture this adoption and growth that is particularly a function of income. Usually it's by time, but there are some examples like this where it differs. Okay, and so this particular example is being drawn into sort of a larger scale model. And so what I'm demonstrating here is essentially a series of different models. So this is so roadmap, there's GChem message, and then MOMO. This is a International Energy Agency, so IEA has this model. And so these are all sort of large scale, these are all large scale transportation modeling, transportation system models that take advantage of diffusion models that get integrated into sort of a larger scale system. So I'm not going to go into the details of how this works, but this is more just as a highlight to show ways in which your diffusion model can actually be incorporated into sort of larger system models. There are applications of these models that are being used through a whole different sets of sectors and companies that use them. This is a particular example from Shell, where they're using diffusion models in order to figure out deployment of different technologies, again, on the basis of using historical patterns to figure out what the sort of future consumption of energy is going to look like. And it's always very interesting, you know, taking some of these older studies and sort of seeing how well they predicted the actual use of any particular energy or technology in the future. Usually you end up with one or two people correct, and there's a couple nice examples of this where in retrospect we look at it and we say, oh, these guys got it right, but I don't, sometimes I almost think that it's more a function of the fact that there's so many people making these forecasts and projections. But there are important lessons to be learned from that. You can see what it is that particular modelers got wrong or right, and what sort of assumptions kind of drive those results. Okay, so let's talk about a specific example and its application and how we might sort of use it. So the basic shape of technology adoption, so non-cumulative, I'll say what that means in just a second, looks something like this. And this is really a nice sort of generalized shape that gets applied to any number of technologies, whether it's, you know, TVs or cell phones or cars. I've seen this type of approach and assumption be applied to a huge sort of plethora of different technologies. So this is looking like a sort of normal distribution, which you can sort of characterize with some kind of logistic function. They tend to characterize different portions of this curve into categories of people who adopt this technology. And because it's just like a regular normal distribution, you need two parameters, right? For a normal distribution, you need the average time it takes to adopt, which is your T star down here, and then your standard deviation, which is characterized, which they use to characterize the different adopters. So the first people who will adopt the technology are kind of your innovators, and then you've got your early adopters, your early majority, your late majority, and then your laggards. And so this is essentially a way of figuring out, you know, where you are and what types of people are adopting the technology. And it actually, it kind of goes both ways. And so what I mean by that is we can characterize, if we know something about the parameters, we can say, oh, like, okay, so what I mean, so if I'm talking about electric vehicles, for example, let's say we know the mean time to adoption, T star, let's say that's like 2030. And if I know something like that, then I can say something about the fact that you know, where we are right now means that the people who are buying electric vehicles are in the early majority, or they might be in the early adopters. And conversely, you can say, oh, if I know in general these types of people are early adopters, or these types of people are early majority, based on what we know about these about people who adopt technology in the past, then you could also use that information to conversely say that means that, you know, T star might be X years in the future. And so this particular approach is really common, especially when you're doing qualitative descriptions about when you think things are going to peak and what types of people are adopting the technology. This is a really sort of handy framework for characterizing those adoption patterns. Okay, so I did mention what I would say about non-cumulative. So it just means that if I look at this plot, it's saying, for the example of like electric vehicles, when will a person own their first EV? So cumulative, it would look different, right? And so it would look something like this. So if the non-cumulative curve looks like this, which will tell you the rate at which people will accept the technology, then the total amount of people who own the technology will look something like this up until it saturates the entire population. Okay, and so the way that I can generally characterize a function of this shape is with a logistic sigmoid. It looks essentially with this kind of functional form. And so you can play around with a basic sigmoidal function. I have some links down here. And essentially there's two parameters, right, for your mean and your variance, which characterize your normal distribution. And then you can see how that affects the cumulative amounts in the blue here. Okay, and so with this quote, so the market for new good grows according to a logistic curve if the number of buyers adopting it at a given time follows a normal distribution. Okay, so that's exactly as I've been describing. So we can see the cumulative adoption in the blue, and then the like this would be kind of your annual new adoption, or whatever time period new adoption in the purple. Okay, any questions about this? I'll stop real quick. All right. So other S-shaped penetration curves. So this is a simple logistic where they may have more parameters. So in this previous case, you've got this sigmoid function that looks like this, and it's always going to be shaped something like this. But if you want it to be a little bit more customized, like maybe the inflection point isn't at halfway, maybe it's earlier, or maybe it's later, or the rate at which your curve goes upwards. You know, it could be really long, or it could be, you know, really short. So the way that shape is defined, it's a little bit less flexible in this particular equation, and it's a little bit more customizable here. So the K It represents a market cap. And so instead of going from 0 to 1, let's say you wanted to know like, or you wanted to set the actual number of, for example, like vehicles. That's what you could represent with K. You've got a growth rate, share in your base here, and then these time periods allow you to actually figure out, what your adoption would be in a particular year. So if I were doing it on an annual basis, year of sales would look something like that. So this some examples of S-shaped penetration curves for predicting vehicle penetration. So as I mentioned before, this is something that we had looked at for vehicle adoption for different types of technologies. And so this is the type of thing that you would be able to calibrate. And so, for example, if I have a sort of well-developed curve that looks like this, and you believe that that vehicle technologies are going to get adopted in a similar pattern, I can calibrate the model to a particular curve that does have a lot of data and apply it to maybe other technologies that are sort of just beginning, and sort of figure out what the adoption rates are going to look like for that. One of the things to keep in mind is that the growth rate of technology is not constant throughout the product's life cycle. And so sometimes you may have examples that may look a little bit less straightforward. So something that looks like this, right? Or something with multiple humps, or really sort of long tail, as you see in this particular example. So the model definitely isn't perfect, but in general, because technologies tend to look similar in the way that they're adopted, it is a fairly accepted practice to use these sorts of models to get at the diffusion and adoption of your technology. Okay, one more that I'll talk about. This will be sort of the last example, is the vast diffusion model. So this is probably one of the most commonly cited versions. It actually only has 3 parameters that sort of help define what the curve looks like. You've got your, 4 parameters, not 3. Your M, which is the pool of potential adopters. This is the same thing as K in the previous model. So M will tell you kind of like your market cap or your market limit. There are 2 parameters which are meant to describe the pattern of adoption among 2 segments of population. So one is your innovators. Those are like the early adopters, and then that's described with this parameter P, and the other are imitators, and that's described by a parameter Q. And so we'll see how that sort of ties together in just a moment. So the imitation rate Q is multiplied by how many people already use the product N. So this is the sort of form of your vast diffusion model. So this big N is cumulative sales, and then this is period sales. So like if it were every year, if T represents every year, then it would be annual sales, which is typically how these things are measured. And so what I would encourage you to do is check out the Bass diffusion calculator. There are a number of them available sort of online, or you can build your own in Excel and play around with your parameters P and Q and M, and see how that affects the adoption rate. So with your period one, like I was saying, it looks somewhat like a normal curve. It's not exactly like normal in a Bass diffusion context, but these are sort of intimately sort of related. And so the way in which a lot of this diffusion modeling happens is we have, I guess there's sort of two general approaches. Either you'll have some segment of data that you have available, and then I want to know sort of how that's going to look like in the rest, right? And so the way that you would do this is that you can simply feed in the data into here, right? You can calibrate it to your NT or this one, and then you use regression-based approaches. I mean, this is a regression-based approach. You're using like a maximum likelihood estimation or some calculator to figure out your values of P and Q based off of what you observe in the data here. And once you have that, once you've solved for your P and Q, you can then plug in values for your T that will generate the rest of this curve. The other way to do it is that you have data on like an entire curve for a different technology. This is actually really common as well. And you figure out your P and Q from that, and then you can apply it to whatever sort of new technology that you're interested in looking at. And sometimes you'll even be able to find that in the literature, where they'll say if you have values something like this or like this, so you actually have ranges of estimates already that exist in existing studies for your P and Q parameters, which you can then directly kind of translate into a curve that describes the technology that you're looking at. Does this make sense? All right. Okay, and so that's kind of one of the most common diffusion curves, the Bass diffusion model. There are a couple other S-shaped diffusion models, right? Again, leveraging the fact that a lot of the adoptions look like they're S-shaped, that are symmetric, so cumulative normal or logistic, which we mentioned. There's asymmetric, which is like a Gompertz, or there's other sort of flexible distributions, a cumulative log normal or Weibull that can be used. Yeah, and so these diffusion models again leverage the fact that that the technology adoption patterns look relatively similar, and so we can use that to figure out what adoption of the technology may look like for us in the future. And maybe the last thing that I'll mention for today is that that there are some sort of criticisms and caveats of diffusion models to keep in mind. So artificial restriction for symmetry and midpoint inflections. And so depending on your diffusion model, you may have specific parameters that determine these. And unless you have really good sort of qualitative or quantitative reasoning, a lot of times these end up being kind of arbitrary. Yeah, especially like if you're just assuming like a cumulative normal, then your inflection point always happens at 50% adoption, which may or may not always be the case. And so you may need to use more sort of specific methods if you have information about why it might be different. Otherwise, you end up just making that sort of assumption. Assume diffusion processes are independent and no considerations of simultaneous diffusion of multiple innovations. And so this is particularly the case for like, so in the transportation example, like if I were doing that adoption, and let's just say I assume that electric vehicles are going to be dominant, and one day all your gas cars are going to get replaced with electric cars. Well, I've made this assumption that the market penetration, the big M or the big K, will end up being saturated with electric vehicles, and so that shows you a particular pattern. But what happens if you have a new technology? What happens if you have like hydrogen vehicles suddenly come in? And so unless you're specifically accounting for that, the simultaneous diffusion of technologies and innovations is not sort of well characterized when you're looking at these diffusion curves. Diffusion models are demand models and don't explicitly take into account like supply restrictions. And so that may be a problem in which you may have demand for the technology, but there's not enough product to meet that demand. That's going to mess up your diffusion curve. And this actually speaks to, I think, kind of like a higher problem, which is that you're kind of assuming that there are factors that will make the technology that you're interested in basically look like all the other technologies, and that there's other factors that don't influence them in different ways. And so what are some of those things? So for example, you could have a policy that would maybe accelerate the transition because they have like specific regulatory requirements to say adopt a certain number of electric vehicles, or you could increase demand by providing incentives to consumers to transition to that technology. And so if I'm basing the adoption curve and adoption rate of like electric vehicles based off of some other technology that didn't have a similar type of policy, you wouldn't be able to replicate the effect of that policy on the diffusion. And so that's one reason why sometimes you have things like a regression-based approach that's sort of better at doing these sort of forecasts, because sometimes they will be able to measure and take those things into account. The diffusion models are fairly simple and straightforward and easy to kind of deploy and get results, but they don't have a lot of the like complexity about getting details specific to the technology into the modeling platform. And sometimes it is possible to do that. But that's oftentimes when you are deploying models, as I was talking about before, that are like really specific to that technology. So you have like a technology specific diffusion model that tries to take into account some of these external factors that may make them look different from other technologies. Diffusion models sometimes can freeze the attributes of new technology at the time of introduction. And so if there's something systematically different about your technology over time than what it looks like in the beginning, especially relative to other types of technologies which may not have that sort of difference, then again, you may be missing on characterizations about your specific technology that looks different from other technologies that you're basing those diffusion patterns on. And so that can also be problematic when you're constructing these sorts of models. Okay. Oh, does someone have a question?
Yeah. So quick question. Are diffusion models essentially only long-term, or just to correct, let's say, the issue of, say, simultaneous diffusion of multiple technologies? So using the EV example, can be let's say that if you're looking at adoption over the next 10 years,
Yeah.
can I have 2 diffusion models for, say, and split the time period into 5-year blocks, where I can then change the assumptions in the second 5-year block to try and look at how that diffusion would happen, rather than, say, looking at it as one single time period of 10 years. That would potentially then also allow me to change attributes of the technology, right, with time.
Yeah, so that's an interesting question. I've never heard of anyone doing that. Probably one of the difficulties is that if I go to this set of equations, so what that would mean in practice, for example, is that you would make this equation, you would figure out your P and Q, you draw the curve up to a certain point, and then you want to change it, which means that now I have to have different values for my parameters for, say, a second sort of time period, right? So if I wanted this now to do something else, and I guess I'm not certain how you would go about finding new values of P and Q. Like it would have to be some kind of arbitrary approach for figuring that out, right? Because you don't have any additional information 5 years later, especially, I mean, if it's like a projection of like 5 years later. So I would say, it sounds like it's in concept a pretty interesting way to deal with that issue, but I'm not sure how you would do it. And what I would also say is that typically, yeah, these diffusion models really are meant for kind of long term. And you don't really see diffusion models being just deployed for like a couple of years. They typically think about the trajectory of the technology in society as a whole, and they want to think about it for beginning to end of like where or it's not where, when people will adopt that technology. So I don't think I've seen too many examples of like short-term uses of the diffusion model. And I guess I don't want to like disparage the diffusion models too much. I feel like I don't want to be like a naysayer. You know, for all of its shortcomings, these diffusion models tend to be pretty nice because you essentially are saying you're making some kind of projection or forecast, right, of this technology, and ordinarily, like for new technologies, you don't have much to go off of to say, hey, in like 50 years, I think that we're going to have this many, electric vehicles or cell phones or whatever. But it's an informed approach because, like, again, under the theory that technologies tend to get adopted in similar ways where they sort of diffuse through society, then you you do have something to go off of, where you're saying, well, if EVs get deployed like all these other technologies that I can point to, then we can be, you know, fairly certain then by X year they're going to be, you know, Y% of the market. And that's really kind of the power of the diffusion model, is like, you know, you're making a lot of shortcut assumptions to be able to quickly and give like a high level sort of answer about what the technology is going to look like.
Yeah, okay.
Hopefully that helps.
Yeah, thank you.
Can I ask a question as well?
Yep.
So you talked a few times about how if you're trying to study like a new technology, you can use a diffusion curve from a different type of technology and kind of put your new technology into that curve.
Yep.
So it sounds really cool, but I'm curious, like when you're submitting it to a journal, reviewers would not be particularly happy about you borrowing a curve. So I'm curious how you justify that they're similar enough, like what metrics you have to use to justify that that curve specifically fits your technology.
Yeah. So oftentimes this is where you'll end up doing a lot of like uncertainty or scenario-based analysis, where there's a couple like qualitative things that you can say, and there's a couple like quantitative things that you can say. So on the qualitative side, you could say something like, okay, for electric vehicles, you know, maybe the closest example that I can think of is like hybrid vehicles, right? Which is kind of in a similar vein. You know, you can make these qualitative arguments that the technologies are similar in that, you know, compared to the incumbent technology, they're more efficient, they have higher prices, they both have higher prices, that sort of thing. So one of the justifications is making sure that the technology that you're comparing to is somewhat similar to the one that you're actually talking about. And then the other thing is that you provide a range of scenarios where you compare several different technologies, and you can show some sort of robustness in the results. And so those are maybe some of the things that you could do to help alleviate the fact that you're kind of just like leveraging other technologies. But what I will say with regards to your kind of specific example is that the context of like what you're trying to say really kind of matters in this case, because oftentimes these diffusion models can be more sort of starting points for other sorts of analyses, right? And so maybe I want to say like, what are the emission impacts from doing from electric vehicles, you know, 50 years into the future, and you can have a whole bunch of other analysis about you know, how they're getting driven, how they're getting charged, what sorts of power they're drawing from, what are the emission rates from those power sources, right? All of that in this really big model. And then the sort of starting point is that the like actual number of vehicles is coming from like a diffusion model, something like that. And so you're not necessarily using the diffusion model in and of itself to say like, this is what I think, this is what the future is going to look like. You're saying here are like possible futures based off of like a commonly used tool with this sort of justifications for this sort of justifications for why those parameters are what they are. And so I think that you will typically get more pushback in, say, like peer reviewed literature if you are really just relying on the results of the diffusion model themselves as kind of like the final thing. But maybe it's a little bit more acceptable if it's, you know, if it's not meant to demonstrate the exact kind of like projection, and rather it's like sets of scenarios. I think that when you do want to have like a adoption model, that like a standalone adoption model that's really focused on the outcome, as opposed to what I was saying was part of a larger model, then you would probably need to end up getting a whole lot more sophisticated with your diffusion model. And so, you know, with the Bass diffusion model, this model itself is actually fairly common. So I have actually seen studies that basically just run this and to show projections. But I think a good study would take this and maybe expand it to also think about other issues like policy interventions, which you could actually insert into here, right? There's there are different ways of doing that. So you could like add more parameters than just P and Q, where you have more terms that like tack onto here that describe other things that are happening. And I think that's generally where the contribution is these days in that sort of adoption modeling, where you are modifying diffusion models to be really specific to the technology. Yeah, and so yeah, typically relying on other P and Qs from other technologies is basically a shortcut for figuring out what the adoption levels are going to be. But for contributions, it's going to be that thing, or it's going to be like I was saying, where you take a part of the existing data to calibrate your P's and Q's, and that's and that would be sort of more contribution, because you're actually empirically figuring out what the P and Qs are. And actually, now that I'm saying that, I actually do have one paper that has done that I wrote quite a while ago. And there was some of that pushback, but because you know, we're contributing into the realm of what P and Q is using real data, like I think that was sort of acceptable. So.
Thank you. I had another assignment related question.
Okay.
I was just looking on Canvas and it doesn't look like there's a place to submit the project description. Should we email that to you, or will it be on Canvas?
I generally do it by email, but actually I'm going to put it up on Canvas, and I'll make an announcement to do that as well.
Okay, sounds good. Thank you.
Yep. Okay, and that was actually my last slide. So why don't we end here for today? And same deal as always, I'll stick around for a couple minutes for any other questions or comments that folks may have about this lecture or about the project proposals. Happy to chat. Otherwise, I will see you guys on Wednesday. And don't forget that homeworks will be due Wednesday at midnight.